It consists of this plastic matrix, which holds these rectangles of an ordinary glass mirror. And now you will see how a similar composite mirror focuses solar radiation to this point.
You can easily calculate that the total cost of manufacturing and installing these mirrors is between $15 and $30 per square meter. It is about 10 times cheaper than these mirrors, which are used to produce large amounts of thermal energy and electricity. It is obvious that such a radical reduction in the cost of mirrors makes their electricity cheaper than from solar panels or from thermal and nuclear power plants. And the thermal energy from that mirror is cheaper than heat from conventional solar collectors. That is why let's look at what problems will be encountered by a startup that aims to cover many square kilometers with similar cheap mirrors to produce huge amounts of cheap electricity and heat. We take an example from this Indian solar plant, where these concave mirrors focus solar radiation into these receivers, which absorb the radiation and convert it into steam for a turbine. It is obvious that this point should be the location of a similar receiver. This dark surface will be heated by solar radiation and therefore heat the liquid, which must circulate through these tubes. We also understand that the mirrors should form approximately such rows, and here we see 3 receivers of one short row. For example, this receiver is the focus point of the solar radiation of these mirrors, but the number of these mirrors should be several hundred, and these dimensions should be several meters. This pipe is a path for the circulation of the liquid which is heated by the receivers, and the pipe must be covered with thermal insulation. The receivers must move from morning to evening according to the movement of the sun across the sky, and my previous videos often showed how solar radiation from mirrors hits receivers during a day. In addition, my future videos will show this experiment for different months where mirrors were installed in a plastic matrix. Also, my previous videos often showed this device, which can simultaneously move several dozen receivers of one row. In addition, we must change the location of the receivers in this way approximately 10 times a year, and now I am showing how I do it in my solar station, and we see that it is a simple and quick action, about 5 seconds for several square meters. These 2 old videos described several types of receiver mounts, where this is the first type, this is the second type, and this is the third type. So, that startup should have machines for cutting mirror sheets into rectangles with dimensions of approximately 20 or 30 centimeters. Also, it must order or manufacture these plastic matrices, and it must have production lines for making cheap receivers, their mounts and their pipes. In addition, the startup must have machines which automate the installation of mirrors and receivers to reduce the total cost of construction to this level of cost of mirrors and this level of total cost of receivers. If that startup more or less achieves these goals, the cost of its solar thermal energy will be like this: 1 cent per kilowatt hour, and it is 2 or 3 times cheaper than the cost of heat from these conventional solar collectors. It is not surprising, because the total cost of manufacturing and installation of these solar collectors is approximately 5 times more than the total cost of these mirrors with receivers. Therefore, that startup could create competition for these solar collectors, which heat water for heating greenhouses. Or our receivers can heat an antifreeze liquid, replacing the solar collectors, the thermal energy of which is used for district heating of cities. Or we can remember these solar collectors which heat water for various industrial processes in factories and plants. At the same time, our mirrors not only have a lower cost but also high heating temperatures for generating steam and other industrial processes with temperatures up to 300 degrees Celsius. But let's assume that the startup set a more complex goal: to build solar power plants with millions of mirrors over an area of tens of square kilometers. We take an example from the type of solar power plants, about 100 of which have already been built, and now I will quickly remind you how they work. When the sun appears, its radiation is focused by the mirrors and heats thermal oil inside these receivers to temperatures of almost 400 degrees. This hot oil moves to the center of the solar plant, where its proportion produces steam for a turbine, which generates electricity. The rest of the oil comes to such heat storages, where the oil heats tens of thousands of tons of molten salt to a temperature of almost 400 degrees. A few hours later, in the evening or at night, the thermal energy of the molten salt will produce steam for the same turbine, and this is an advantage over solar panels, which require expensive electrical storages to sell electricity at night. So, millions of similar cheap mirrors of our solar power plant must cover tens of square kilometers, and the receivers heat thermal oil to a temperature of about 300 degrees Celsius, and the oil moves to heat storages. One of my old videos described various types of heat storages based on concrete, sand and other cheap materials, which are heated by the thermal oil to a temperature of several hundred degrees. They are very cheap heat storages, and therefore they can be very large, hundreds of thousands of tons. Therefore, their thermal energy is enough to operate the turbines for several non-sunny days in a row, while this possibility for the combination of solar panels and electrical storages leads to an increase in the cost of their electricity many times. Moreover, solar panels are not able to transfer their energy from summer to winter. At the same time, this from my video described the heat storages from millions of tons of soil or waste, and they are heated in the summer to return the thermal energy in the winter. You may notice that the mirrors can be placed on a berm, and this angle should be approximately equal to the geographic latitude. Nevertheless, my future videos will show this experiment, which allows reducing that angle or abandoning the berms, and for example, this case occurs at 50 degrees north latitude. It is also clear that no berms are needed near the equator, but in cases of more northern regions, that startup must create machines for the formation of berms along the west-east line and level their southern slope for the location of those plastic matrices for mirrors. This is an alternative to a berm, where we place our mirrors on steel structures similar to solar panels. In addition, this alternative does not have the grass problem that occurs when our mirrors are placed on a berm. It is obvious that the startup should solve this problem, for example, put some kind of fabric under the plastic matrices, or create machines which simultaneously wash mirrors and mow grass. Of course, my plastic matrix is too weak, and that startup needs to find a stronger plastic structure with a few kilograms of cheap plastic per square meter. These latches are needed to keep the wind from moving the mirrors, but we can use glue instead of the latches. Also, it is possible that resistance to winds will require increasing the weight of the plastic matrices, for example, placing concrete tiles in these gaps under the mirrors, or filling some of the gaps with concrete. Another problem is the possibility of large hail, and therefore the startup must choose the thickness of the glass layer of the mirrors and be ready to install new mirrors after an abnormally large hail event. I remind you that my YouTube channel explores many different types of cheap mirrors, among which you can find more promising ones that can provide cheaper thermal energy in the future than this mirror. But this type of mirrors requires little investment for the startup, while other types of mirrors will require additional research costs or more expensive production lines.